Okay, guys. Let's get started. Excuse me. Okay. Welcome, guys. Beautiful exception waiting for me here. And also, this is in Stopes, but also in Fairsec. So we can pick our favorite exception basically at this point in time. And I think I like this one. I prefer this one definitely compared to the previous one. So let me see what we need to do here. This is actually weird. Why did this fail? Aha. That's why it failed. So actually the structure is okay. It's just that I left this one needs to be deleted. And now this should work, guys. Let's go here. We should have cached all of the data for non-HBS inside of the LID directory. So here is the LID data, and exactly we are already hitting the non-HBS. So that's cool. So now let's kick it off. Put a breakpoint here. This downloading should be fairly fast. Actually, this is not downloading. This is okay. What is going on again? We're just trying to extract the German files here. Not the directory. Aha, txt. Bad corporal list. Oh my god, okay, again. I just have some residual files I have to delete from the German data. This one as well. Now it should really work. Here we are. Kick it off. Please don't fail. Please do not fail. Stop sampling. Seems it's working. We can finally kick off the run. Just a bit more. By the way, fun fact, I'm reading Elon Musk's biography from Walter Isaacson. I think that's the name of the guy. Walter Isaacson. American writer and journalist. Exactly. It's a great book so far. The guy had a super tough childhood. Good morning from San Diego. Nice. Hi, George. Awesome. Thanks for letting me know for the audio. Hope you're doing well, man. Okay, here we are. Next step is filtering. Here we can see the progress. Ever since I went to China, I started reading many more books than before. Like over the last years, I was mostly consuming podcasts. I had a part of my life where in high school I was reading a ton of books, and then life happened. I was obsessed with reading papers and stuff. But like I finally found back my old habit of reading before I start working and in the evenings before I go to sleep. And like I feel super like inspired, and I kind of found that lost, forgotten like passion for reading books. There is just definitely something special about reading books, and the amount of depth you can get from a book is definitely also something I appreciate now that I've listened to so many podcasts across so many genres and heard so many people. So like books are definitely like something I'm gonna be super bullish on over the next months and weeks. So yeah. Okay, well this is running. Let's go back here and try and figure out what's going on with the try and see what's going on with filtering. Dedupe. Okay, let's maybe try and comment out everything related to debugging. Maybe it's just debugging stuff. Let's kind of make that assumption quickly, even though it doesn't make any sense. Okay, if we do this and we run filtering, let's see what happens now. What? It's working now. So it was it was debugging. It was some of the change I made recently. Okay, let's see what's up. Let's now try and retroactively add line by line. Let's add this one. And then we can add this. So we can let's go step by step. So this is completely confusing, so I have to understand what's going on. Is it gonna fail now or not? It's not. Okay, let's go beyond. Let's add this. And let's rerun. Oops. It's wrong file. Filtering. Okay. There seems to be something there. Let's go back. Undo. Something here is causing the issues. Oh. Okay. I think I know what we have to do, guys. We have to... Am I using anything from the self method? No, I'm not. shingle set. This can be completely outside, right? This doesn't need to be doesn't need to be the method of this class. It can be just outside. Now let's just update all of these. Nice. Okay, that's first step. The next one is grab the worker and extract it outside. So what was happening is that because this is a self method, they tried to pass some of those internal member variables, and one of those was a file handle, which is apparently not pickable. So this one was failing because of that. And I think with this, we should be good. That's it. So I think now, first let's make sure that the previous state works. Hit run. Let me see how the other code is progressing. Okay, almost done. Run. Okay, it's working. Let's now re-enable this. And this. And this. And rerun again. Okay, I'm again in a wrong file. Okay, here. Run this file. Come back to dedupe. Put a breakpoint here. And it works. Voila. Awesome. Fix the bug. Okay. Remove this breakpoint. And let's wait until we hit this line here. And let's see whether this is gonna work. Really excited to see how this works. Almost done. Okay. Hit run. Here we are. And enter here. Okay. I'm running multiple things in parallel. Let's go. This processing will take a while, unless it fails. Enter here. Write. Wait until we hit this line. So it's equal to 40,061. Which is not smaller. Oh no. Oh no. Wait. Wait just a second. Index to data set. How did I end up with this big of a number? Result gave me back a huge number, even though we're using... Now this is weird. That's because we have a ton of... Nah, something went wrong here. I think I just forgot to delete the output directory. So I'll have to rerun this. Let me think for a second. Maybe I can skip having to rerun. If I see 4616, if I see that one here, no, we'll have to just run everything from scratch, guys. I have to delete the whole thing. Go to filter, rerun. Okay. Almost there. Let's see what else we've got. So almost done with fuzzy, almost done with training fast text. So that means the next step will be, and I debug this as well, and this is not necessary. So we need to train the system. These are the next steps. And then we go here to prepare the data. Okay, getting closer to this. In the second iteration, we can just improve stuff a bit. Iterate on the model with 615 million parameters, get more data, train a tokenizer. And at that point of time, we're gonna start scaling up. But at that point of time, we also need more compute. Let me just see, how long was the original transformer trained? "12 hours on 8 P100 GPUs. I think I have more powerful GPUs than these ones. The big ones were trained for 300,000 steps, 3.5 days. I wonder how these two compare. Wow, RTX just is so much better. Here though the trend reverses. Okay, this is still running. Should be done very soon, this one. Okay, let me just kind of go in my brain through the next steps. Assuming this all works nicely, we have the whole filtering pipeline in a decent shape. And I'm about to train the HBS versus non-HBS model. So I think we have everything we need for the first iteration. And then we'll have to experiment a bit with setting different hyperparameters to tune the filtering pipeline. The length filter, the symbols filter, the LID filter. This one we'll be using this proprietary new one that I'm about to train. Dedupe and fuzzy. There's nothing we can do about this one. We can tune the fuzzy one. These are kind of our levers, like fuzzy, LID can get better, and we can tweak the settings of these ones. And then the next big step will be to just train a tokenizer, because the current one supports over 200 languages, and we just need a couple of languages for what we're currently training. And so it takes a ton of space. I think around 200 megabytes comes from the embedding table from the SPM 200 tokenizer. So that's the second iteration here. Train the tokenizer and also start using Cyrillic and Latin. More data. So more data, better tokenizer, smaller and dedicated. And that will allow us to also expand to all 5 languages. So meaning Serbian Latin and Cyrillic scripts, Bosnian Latin and Cyrillic scripts, and Croatian Latin script. Let me see how many lines Wikimedia has. 186,000. Let's see where we are. We're processing 140. 40 more thousand to go. And 67% here. Okay, I'm gonna zoom out a little bit, check some, I have to do some personal work here while this is running. Okay. Let's go. Run. Finally. $40,061. Again, same issue. This is weird. This should not happen. Oh no, actually wait. This should happen because we have Wikimedia, which is huge. And we probably had 8 workers running here. So then the question is why is index to the asset so small? What did I mess up? Let's see. Aha. So what I messed up is that well, actually nothing. Let me just a second. So we have 3 data sets. That's fine. Global offset. Tells us number of lines. And then we never enter here. So I think I just have a messed up logic. Everything else is good. So I have to find the key. I have to go all the way to the last data set. We are in the 3rd bucket. We should fetch the 3rd data set, but instead we are fetching the 1st one because this logic is not good. So what I need to do instead is maybe we need to go in reverse. That's easier. So go in reverse. Just a second. So this is a dictionary. So we need to do keys, sorted, and then we need to go in reverse, I think. Let me think. So we're trying to find where this candidate is in. Out of all of the data sets we have, where should we place it? So we need to find the band, the right band for this one. If you're smaller than pass. I know I'm not using the right data structure. There must be something that's much easier to do this. Yes, we can go in reverse, and that's the easiest solution. I'm not gonna overcomplicate. Reverse Python. Or just sort in reverse. So go through those keys in reverse. Okay, and now that we have this, we ask, are you bigger? Are you smaller? If you're smaller, then ignore. I think this will not work. Otherwise, you're bigger, you enter here immediately. This should not work. Stop. Rerun. Let's just speed things up a bit by going here and commenting out this whole logic. Waiting to hit this breakpoint. So key is this big. And this is even bigger. So because of that, we immediately grab index to dataset. Aha. Wait. We can't do this. We need to do, no, actually this will work, yes. We grab the data set and then we grab the map line number to byte Then why do we have skipped all of the lines? Okay, let's see. This is the offset. And it failed, of course, because this key does not exist. So line number was not collected properly. This did not work. It's line number to byte offset, not the other way around. That was the error. Let's go. Key is 8000 and this is this big. In this iteration, key is this big. So this number, which is 4156, is between this number, 463, and this number. And that's why we enter in the second bucket. And now we grab the mappings. We grab the offset. We get the offset. We open the files. We seek. We read line and normalize. Does Tom know where I live? Dali Tom znak drži. This is perfect, guys. This worked. This fucking worked. Now, the final question is, given the offset, let's just confirm ourselves. So, given the offset is 3693, and the data set is Tatoeba, let's confirm that Tatoeba 3693. Here it is. Tatoeba. So here is Tatoeba. And we are looking for the input file, which is this 3693. Did I get it correct? Does Tom know? Wait, just a second. This might be just indexing thing. So the index here is 3694 because we are zero indexing here. 94. Does Tom know where I live? And that's it. So we picked up the right file, and here as well. Huh. That's it. Perfect. And we just keep on repeating this. Flush. And then remove. So let's see what we've got as a result here. Here it is. Here are some results we got so far. Perfect. Nice, guys, this is perfect. Let's just find something. When will Japanese classes start? When will Italian classes start? When will Japanese course start? So these are very similar. Maybe it's a question of whether we actually want to filter them out, but this is definitely working properly. Nice. Let's see this one. What would you like to know? I'd like to sing with you. I'd like to buy a car. I'd like to leave now. I'd like to thank you for your help. I'd like to see you here. I'd like to buy a car. Yeah, this is not perfect. I took the first step. I took the first step. I took the first step. So the reason we haven't filtered these ones out with exact duplication is because the Serbian side, because Serbian is such a morphologically rich language, the target side is always different. And that's why we didn't filter these out, but this is perfect. But the target side that's why exact morphological. Awesome. That was super cool, guys. Let's let it run a bit. Oh my God, this is a lot. Chapter, all these are similar. Nice. I'm gonna stop this and we can submit the changes. That's what I want to do now. While we're still waiting for the LID data to process. This is kind of slow. It's very slow. But we're almost done. let's kind of submit this code. Filtering temporary. Let me see what this one does. Stop words. Let's just delete this. Okay, so the only thing we care about is inside of filtering. Let's quickly just skim through the changes. First things first, dedupe. I just moved these outside of the class. Same here, I didn't change anything else. Boolean, we have the logic for debugging. Same here. I want to uncomment this one, of course. Maybe we need to fix this a bit. And that's it. So fix this and uncomment. Uncomment this. And this logic is kind of nasty. Let me think. This was more for my understanding. So we don't really need this check. Okay. Let's continue. File chunker. We build this new logic. It's as efficient as it gets, as we have to read through all the lines. Configs. And filter. Make sure that the counts are always filtering counts. That is, the dictionary always has as value the filtering counts. Change the name of the min hash directory so that we can have separate directories for primary and mine data. And then we don't have to do this anymore because we now have filtering counts as the value always, and here as well. That's it. Let's save this. Commit these changes. So configs, filter, dedupe, and file chunker utils. Okay, we are ready. We just need to wait for this to finish. Why is this taking so long? We're processing English, German, and Turkish. I guess those are these three. Subsampling. And I guess this is not filtering. Okay. Let me see what we have for reading while we are reading this. Let me see whether somebody's asking questions. Hey, Amir, thanks, man. Nice, awesome, congrats. That's definitely very, very more, what would be the word? There are more opportunities, 100%, in software engineering than electrical engineering, although both are exciting. Same story as what I've done. I studied electrical engineering as well. Reading list. Let's skim through this one while we're waiting. Dirt cheap web scale parallel text from common crawl. Parallel text is the fuel that drives modern machine translation systems. The web is a comprehensive source of pre-existing parallel text, but crawling the entire web is impossible for all but the largest companies. We bring web-scale parallel data to the masses by mining the common crawl, a public web crawl hosted on Amazon's Elastic Cloud. Starting from nothing more than a set of common two-letter language codes, our open source extension of the Strand algorithm mined 32 terabytes of the crawl in just under a day at a cost of about $500. Nice. Our large-scale experiment uncovers large amount of parallel text in dozens of language pairs across a variety of domains and genres, some previously unavailable in curated data sets. Even with minimal cleaning and filtering, the resulting data boosts translation performance across the board for 5 different language pairs in the news domain. And on open domain dataset test sets, we see improvements of up to 5 blue. We make our code and data available for other researchers seeking to mine this rich new data resource. Okay. A key bottleneck importing statistical machine translation technology to new languages and domains is the lack of readily available parallel corpora beyond curated datasets. For a handful of language pairs, large amount of parallel data are readily available, ordering the hundreds of millions of words for Chinese English and Arabic English, and in tens of millions of words for many European languages. Mostly government and news text. direct translations. This natural parallelism simplifies the mining task since few resources or existing corpora are needed at the outset to bootstrap the extraction process. Parallel text mining from the web was originally explored by individuals or small groups of academic researchers. Okay, let me just... How many lines we've got? 20 million roughly. And then we shuffle them. And this might take a bit of time to shuffle 20 million. Using search engines, however, anything more sophisticated generally requires direct access to web crawl documents themselves, along with the computing power to process them. For most researchers, this is prohibitively expensive. As a consequence, web-mined parallel text has become the exclusive purview of large companies, with the computational resources to crawl, store, and process the entire web. They mine from Common Crawl, and then using Common Crawl completely removes the bottleneck of web crawling and makes it possible to run algorithms on a substantial portion of the web at very low cost. They use queues from URLs and document content to do the matching. We conduct an extensive empirical exploration. On general domain and speech translation tasks, improves the performance substantially, resulting in improvements of up to 1.5 BLE on standard test sets and 5 BLE on test sets outside of the news domain. And this is, by the way, Amazon work or whatnot. I think this work was related to Amazon somehow, because the person that sent me this was used to work at Amazon Translate project. Nice. And finally we can train. "25 epochs over 20 million lines might be a bit too much. But let's just kick it up. Let's see what happens. Let it run. Aha. Nice, this is like super fast. Let's continue reading. However, it is unnecessary to obtain a copy since it can be accessed freely. In our pipeline, we perform the first step of identifying candidate document pairs using Amazon EMR. Download the resulting document pairs and perform the remaining steps on our local cluster. Our system is based on strand algorithm. Retrieve candidate document pairs from the common crawl corpus. Convert the HTML of each document into a sequence of start tags, end tags, and text chunks. Align the linearized HTML of candidate document pairs. Decide whether to accept or reject each pair based on features of the alignment. For each text chunk, perform sentence and word segmentation. For each aligned pair of text chunks, perform the sentence alignment method of Gale and Church. Remove sentences that appear to be boilerplate. So retrieve candidate document pairs from the common crawl. This is kind of very vague. I'm not sure what they mean by this. Structural filtering. Let's see what they say. We adopt a strategy similar to that of Resnick and Smith. Scans the URL string for some indicator of its language. We check for 2- and 3-letter language codes. Language names in English and in the language of origin. If either is present in a URL and surrounded by non-alphanumeric characters, the URL is identified as a potential match, and the mapper outputs a key value pair in which the key is the original URL with the matching string replaced by a star, and the value is the original URL, language name, and full HTML of the page. For example, if we encounter the URL like this, we output the following. And then the value, website.com, French website entry. Okay. The reducer then receives all websites mapped to the same language independent URL. If 2 or more websites are associated with the same key, the reducer will output all associated values as long as they are not in the same language. As determined by the language identifier in the URL. This URL-based matching is a simple and inexpensive solution to the problem of finding candidate document pairs. The mapper will discard most, and neither the mapper nor the reducer do anything with the HTML of the documents aside from reading and writing them. This approach is very simple and likely misses many good potential candidates, but has the advantage that it requires no information other than a set of language codes and runs in time roughly linear in the size of the dataset. Okay. A major component of the strand system is the alignment of HTML documents. The alignment is used to determine which document pairs are actually parallel, and if they are, to align pairs of text blocks within the documents. The first step of structural filtering is to linearize the HTML. This means converting its DOM, which is the document object model, tree, into a sequence of start tags, end tags, and chunks of text. Some tags, those usually found within text, such as font and A, are ignored during this step. Next, the tag chunk sequences are aligned using dynamic programming. The objective of the alignment is to maximize the number of matching items. Given this alignment, this work defines a small set of features which indicate the alignment quality. They annotated a set of document pairs as parallel or non-parallel and trained a classifier on this data. We also annotated 101 Spanish-English document pairs in this way and trained a maximum entropy classifier. However, even when using the best performing subset of features, the classifier only performed as well as a naive classifier, which labeled every document pair as parallel in both accuracy and F1. For this reason, we excluded the classifier from the pipeline. The strong performance of the naive baseline was likely due to the unbalanced nature of the annotated data. 80% of the document pairs that we annotated were parallel. It's nice to contrast this approach with laser-based approach that NLLB project used, where you embed the sentences into a multilingual model, and then that's how you mine. You're using some similarity metric then to find the similar data points, and those similar data points turn out to be translations. Whereas this is more of a heuristics-based, structure-based approach. The text chunks from the previous steps may contain several sentences, so before the sentence alignment step, we must perform sentence segmentation. They use the punched sentence splitter from NLTK to perform both sentence and word segmentation on each text chunk. Sentence alignment. For each aligned text chunk pair, we perform sentence alignment using this algorithm. Since we do not perform any boilerplate removal in earlier steps, there are many sentence pairs produced by the pipeline which contain menu items or other bits of text which are not useful to an SMT system. We avoid performing any complex boilerplate removal and only remove segment pairs where either the source and target text are identical, or where the source or target segments appear more than once in the extracted corpus. Okay. And then analysis of the common crawl data. Let me see how this is progressing, by the way. Nice. Why is the learning rate going down? It seems they're modifying the learning rate. We ran our algorithm on the 2009-10 version of the crawl. Okay. Table 1 shows the amount of raw parallel data obtained for a large selection of language pairs. Shows the amount of raw parallel data obtained for a large selection of language pairs. Nice. Is it possible that we trained this already? That was damn fast. Okay, I'm really looking forward to testing this one. Let's just wrap up this paper. Okay. Apparently this was a very old paper. I mean, you can tell by the fact that they use statistical machine learning system. Of all the possible parallel text that is actually available on the web, how much does our algorithm actually find? We found that 45% of the neural pairs would have been discovered by our heuristics, although we actually only find 3.6% in our output. If we had included F and E as identifiers for French and English respectively, coverage of the URLs would increase to 74%. Since our algorithms rely on cues that are mostly external to the contents of the extracted data and have no knowledge of actual languages, we wanted to evaluate the precision. To measure this, we constructed a manual analysis of 200 randomly selected sentence pairs. For German and English, 78% represent perfect translations, 4% are paraphrases, and 18% represent misalignments. Furthermore, 22% of the true positives are potentially machine translations, judging by the quality, whereas in 30% of the cases, one of the sentences contains additional content, not expressed in the other. Across 3 languages, let's just read this. As for the false positives, 13.5% of them have either the source or target sentence in the wrong language, and the remaining ones representing failures in the alignment process. Okay. In addition to the manual evaluation of precision, we applied language identification. They use the LangID tool, and they report the percentage of pairs where both sentences were recognized as the correct language. Table 3 shows our results. Comparing against our manual evaluation, it appears that many sentence pairs are being incorrectly judged as non-parallel. Tends to perform poorly on short segments, as we already know. Most of the data is news and government domains. Table 4 gives the top 5 domains by the number of tokens. Where is table 5 or table 4? Travel, government, religious, political. They've done some LDA analysis. We took the English side of the extracted parallel segments for each URL in the Spanish-English portion of the data. This gave us a total of 440,000 documents. Since our system does not include any language identification, this is not surprising. However, it does suggest an avenue for potential improvement. In our second LDA, we compared our extracted common crawl data with Europarl. We then labeled each document by the most likely topic and counted the number of documents from Europarl. Table 6. Okay, we'll check out those tables very soon. In addition to exploring the topics, we also performed additional intrinsic evaluation. Commercial websites tend to contain less boilerplate than encyclopedic. Of useful non-boilerplate sentences found by domain and language pair. In all experiments, we include the target. Okay, they're doing some experiments using Moses toolkit on this data. They train on data and data plus mine data. And then they test, I guess, on a couple of domains. News domain. They use the 5-gram language models. Okay. List of 20 topics generated by the Melit tool, and they are most likely tokens. A sample of topics along with the number of Europarl and common crawl documents. Okay, nothing super useful, guys. We can just skip most of this. The Tatuiba corpus is a collection of example sentences translated into many languages by volunteers. Okay, that's it. Let's skim through the discussion and we are done with this paper. This paper is just a lower bound according to them. Interesting approach. So translate from source to target, and then use fuzzy to see whether they're similar. This is almost like a related work section and not discussion. Okay. Cool, guys. Let's now test this model. If model is none, then we just load it. Otherwise, we have it from before. Okay, let me just quickly reopen this. I see that the linter died. Let me see whether anybody's asking questions. Fasttext basically acts as the language identification system. Helps us to filter incorrect sentences from our parallel corpora. Okay, now let's grab target languages. These are gonna be Serbian, Cyrillic, Bosnian, Latin, Croatian, German, Turkish, and English. Okay. Here is the root, Flores input directory. So what we want to do is go through that directory. Get the path. If some of the target languages are in there, minus English. English is going to be a special snowflake because English is used as the pivot language. So source lang. I think source lang is always going to be English, right? For eval. English, 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 yes. So we grab the target language. Exactly. And if the target language if it's not in target languages, we continue, otherwise we do what? We iterate through the files. If it ends with the target lang, in that case we grab the file, we read the data, open this one, read the lines, and then label it with either HBS or non-HBS. We go through the lines, we just strip them, and we label with what? HBS lengths are going to be exactly. So this is going to look like this. Label, and then here we'll either have HBS if this current language target lang is in HBS lengths, else no HBS or non-HBS. What did I call it? Non-HBS. Non-HBS. And once we have these lines, we basically collect all lines and we extend and then at the very end we save there, and then finally we test. And that's it. Okay. Do eval. True. Train model false. Generate data false. And let's go. Moment of truth, guys. Let's see what results we get from just the first training without thinking about optimizing the hyperparameters. Okay, load the model. This fails because model path is referenced before. Okay, just a second. Let's just move this up here. Rerun. load it. Wow, how big is this boy? Let's see. LID data. Open the containing folder. 2 gigabytes is the HBS LID. No, that's the data set. Wait. The model is here. Oh my god, almost 5 gigabytes. Nice. German. And here is the German language. And we read it and we just add. We grab the lines, extend, and just keep on doing this, and then drop it here. And let's see. Here is the final file. No, sorry, this is. Let me delete this one. We're looking for the one that's inside of LID data. So looking for Flores, here it is. German, Turkish. Let's go. Let's see how this works. Run the test. Print the result. Done. Oh my god. that was 100% accuracy. Precision and recall. Okay. That was good. I'm not sure how that's gonna extrapolate to arbitrary text. Flores is kind of easy, but that's a good start. Kind of scary. When I see something is working perfectly, that's scary. Hi, Mohammed. Thanks, man. Actually, not 30 days, because I've been to China a couple of days ago, so because of that I had a break of 9 days, and other than that I'm just streaming, and I'm going to keep streaming for many more days, so this is just the start. Thanks, Ayub. I'm not sure how I'm pronouncing your name correctly. You're building a computer vision model for non-human underwater drone. That's super cool. Well, yeah, collect data. I'm not sure what exactly are you trying to do with the. Can you explain what you're doing with the underwater drone? Please join the server. I would love to hear a bit more about it. Maybe you can write it down in the channel here as well. They also generated German translated data sets. Precision, not. Oh, I forgot to add. Joe needs to stop on circling pool. First rule is this. Yeah, I guess it's gonna be some combination of heuristics and stuff. Like you have to do some. Have you checked yellow models for object detection? Something like that. Although you'll have to probably do some augmentations that will simulate the optical characteristics of the water environment. Lighting conditions and blur and all of that needs to be done. Okay, let me see one thing. Let's see how we do on Let me just think for a second. So I forgot to add English, and I also want to add data that was not trained. I want to see how the model will cope with that data. How can we add English? So to add English, I want to once open up or if flag is false and file name ends with English, enter. Okay, so this is going to prevent us from entering multiple times. Once we enter, we set it to true, and we never again enter because it's set to true, and we never set it back to false. Let's see the number of lines. It should be roughly 6,000 roughly. Yes, that's it. And let's run. Again, perfect accuracy. So now I'm curious about, let's pick a random language like Russian. Let's go to download Perl Corpora, and let's pick Russian as well. English, Latin, Russian, I guess Cyrillic. Download primary, hit run. This is gonna fail. It's gonna fail because I haven't deleted the eval data sets. Run again. Okay, now we should have Russian as well. So eval dev here is Russian, and this is going to be certainly confused with Serbian, so I'm expecting to get HBS. Russian is going to be considered HBS. Do we have Macedonian language? Macedonian. Okay. Apparently it's included. They are very similar to Serbian. Okay. What was I about to do? I want to evaluate again, train LID, add Russian, Cyrillic, So again, target, read the lines, extend, and do this. Okay. Run. What's the size of this one? Okay, 7,000, that's it. So I strongly suspect we'll now have much worse result. As expected, I would expect to see Russian being predicted as Serbian. So if I open up a sentence like this, I'm like 100% certain that this is going to be, oops, this is going to be confused with Serbian. Oh, but actually, there is one more thing we have to always think about, and that's that we have to process the lines before we save them. So keep that in mind. So let me copy this first. Go to train LID and do model predict on this sentence and print this. So these lines need to be processed. Process lines. Same as here, we need to do the same for when doing inference. Process the lines and then save them. Okay, let's run. Run. Process the lines, save them, predict. This is predicted as non-HBS. Wait. Well, in that case, that's correct prediction, right? Wait. What did we do now? Oh, yeah, I messed up. I can't do this. I would have to process the lines first. Exactly. Run. Wait, if we have 7, 13, this is roughly 7th of the predictions were error, which is precisely the Russian. But like, what's weird is that I'm getting non-HBS here. Okay, let's do the following exercise. Just use Russian. And rerun this experiment, but this time with a catch. I want to go for a line in all lines, and I want to do model predict. Rerun. It's non-HBS. Roughly 50% is errors. Okay. Non-HBS, non-HBS, non-HBS. Okay, I made a mistake because I actually want to do something like this. And line. Run this. HBS. HBS. It mostly says it's HBS. Sometimes it will tell non-HBS, but okay, here it said it's non-HBS, but it's mostly HBS. That's what I expected. Awesome. Let's now use this new system to filter our data and find German, Turkish, and English. That's going to be the goal. A bit of a play with the newest model. On the red circle. Makes sense. Okay, guys, I'm gonna do a short break just to stretch. We've done a ton of good work, and then we can do we've trained this LID, test the newest LID on real data, and see whether we pick up German, Turkish, English. Awesome. Before that, as I said, short 4-minute break. Be right back. Okay, guys, catch you soon. Okay, guys. We are back. We are so back. Let's test the newest model. Okay, so to test the model, we have our HBS data. We have the eval, we have the HBS. Here's the HBS. Okay, so I want to filter the data. Let's go to Stopes. Let's set everything to none. Set everything to null, except for the LID. LID. And of course, length is always there. Okay. Let's link the new LID model. Go here, LID data. Here's the model. Copy the path. Go back to Stopes. Paste it in here. Delete. Paste. Save. And let's put a threshold of whatever, 0.9. But let's modify our HBS filter. So what do we do now? I do the following. Predict. We get the probabilities. Let me just think how we can modify this one now that we have HBS versus non-HBS. So it's a good thing we created a dedicated class here, because now we're going to modify it heavily. Okay, so we predict the line and we normalize. Okay, but the normalization has to be whatever we used before to train the model. And we used process line, and in particular normalize. This is what we need to use. So I guess we'll have to import stuff from whatever is the file in Stopes. Let me find it. So where do we import these from? Let's see which file. Text normalizer. Let's see how one imports it. Okay, like this. Text normalizer. Okay, you already have it imported. We just have to import the white space and the non-printing character. like that. And I think now we're good. We just have to import string as well. Import the string. Okay. Looking good. Just call it normalize. Will that conflict with any of the other methods? I don't think so. Okay. So we normalize, we run the prediction. And then get the key and the probability. And then get the HBS. And same here. Just get the HBS. And if it's smaller than a threshold that this is an HBS, we save it. Guys, that's it. Super excited to see what we catch. Let's go to filter here. Filtering, filter out HBS LID test. That's how I'm gonna call it. And we need to turn on HBS directions, like these three. Go back to primary and uncomment Serbian. And that's it. Okay. So with that out of the way, let's go to the filter. And run. Okay, here we are. Normalize and predict. Aha. Normalize takes one positional, but two were given. How come? Okay, we certainly have some naming conflict here. Does filter have anything inside? No. Aha. Okay, forgot to add self. Rerun. Run filtering. Okay, here we are. HBS, non-HBS. Grab the HBS. That's for source. That's actually good. Aha, I made a mistake here. Wait. I made a mistake because let me just think for a second. Are we always going English to language to target, right? I think we're always going, if we grab a, let's take a look at the HBS data. It should always be English to something. Yes, it's always English to something, okay? So, under that assumption, plus train primary, English is always going to be the source. Yes, okay. So when we know that's the case, then we know that we want to be non-HBS here, right? We want to be non-HBS. And if that's below 0.9, something is off. Okay, this is the final change. Stop the run. Let me see whether I included, did we enable debug? Let me just enable debug here directly. Or maybe instead of changing this in the code, let's just expose debug inside of the config. So here, let's go to LID filter, debug, let it be false. And then let's go to example and set debug to true. Okay. Run. Let's see whether this fails if I manage to forget something. Okay, debug is set to true. Nice. Nice. Let's put some breakpoints here and here. Ah, nice. We already caught the target sentence being English. This is just amazing. Let's just let this run and see what we get. Oh, wait. We have multiple processes and all of them are writing to the same file. Okay, I just caught another error. I caught another error. All of them are writing to the same file. That's bad. And there is no resource protection logic like semaphore or whatever. Mutex in this case is, I guess, more suitable. So we have a couple of options. Either we can have a separate Okay, I think we can just have separate files. In that case, we're good. Make this an F string, and then just create this to be source lang followed by target lang. Okay. Debug LID filter. Let's go again. Run. Okay, this one created a file for Bosnian. This one created a file for Croatian. And okay, let's just let it run. So we have now 3 files. Each of them are logging issues in respective data, in respective language directions. Okay. Okay, a lot of short words, that's expected. Some English words. We should also write down a cause. As opposed to doing it like this, we should mention why are we filtering this. We actually did. By telling source and target. Prefix is going to be either source if this, otherwise source target, and then use the prefix here. If bigger or equal than the threshold, then just source was problematic, otherwise both source and target were problematic. And same logic goes here. And just put prefix here. So if this is bigger or equal, then just target, otherwise source type. I just realized this will never happen, because if it happened, we would have already hit none. But anyhow, okay, for consistency's sake. And also, let's do some protection. Like, what's the minimum length that we want to cover? Because for short lengths, it's really unreliable. Let's say we want to only filter If it's too short, we want to filter out. Oh, but by too short, we can maybe go 40 characters or something. What's 40 characters? That's like... How long is this sentence? This is 40 characters. Okay, let's try something like that. And rinse and repeat. Interestingly, source is here the issue. They think that this is HBS. Interesting. This is not really good. Look at this. This is Greek language. A lot of weirdness. I see Spanish. Okay, let's just let it run and then we can analyze later. We might have to update our model with Greek and whatnot, but let it just run. Let me quickly see whether I don't have any silly mistake. Looking good. Okay, guys. Let's do a bit bigger break and then catch you in the final stream of the day when we will be analyzing this data and potentially retraining the fasttext model so that we can improve it based on the failure modes we observe. Okay, that's it. Catch you in the next one, guys. Keep an eye out for the open NLLB channel. That's where I'll be posting all of the updates. See you later.